Welcome to the Deep Dive, where we take the stacks of sources you sent us and really pull out the knowledge nuggets you need. Today, we're tackling an absolutely crucial topic for conservation. It's about the rapidly shifting and sometimes tragically diverging fate of fish biodiversity right here in U.S. rivers and streams.
Yeah, we're doing a deep dive into the findings of this really significant paper. It's led by Samantha L. Rumschlag, and the title is Diverging Fish Biodiversity Trends in Cold and Warm Rivers and Streams. It's a massive study looking at decades of data, and our mission today is basically to unpack its surprising, and I have to say, in some cases, truly alarming conclusions about how these freshwater communities are changing across the contiguous USA.
It really is. It's hard to overstate the gravity here. I mean, freshwater systems, they cover less than, one-tenth of 1% of the Earth's surface?
Tiny fraction.
Music.
Right, but they house over 18,000 fish species. That's nearly 26% of all vertebrates globally. Yeah. So, these fish aren't just abstract numbers. They are absolutely foundational, cultural, economic, and ecosystem resources. And the problem is their biodiversity is globally under threat.
Okay.
And for the USA specifically, this research really pinpoints the two primary drivers, or at least two major ones, behind these rapid trends. The first one, maybe predictably, is climate change. Specifically, it's manifesting as quickly warming water temperatures.
Right.
And the second is human intervention, particularly the widespread introduction and sustained stocking of certain game fish species, many of which aren't even native.
Okay, let's unpack the sheer scope of this research first, because that scale, it really gives us confidence in the findings, doesn't it?
Absolutely. It's impressive. The researchers harmonized federal biomonitoring data sets. We're talking EPA and USGS data here.
The big ones.
Yeah, the big ones. And they integrated data across nearly 3,000 unique sites, 2,992 to be exact.
Yeah.
And 389 species, all covering 27 years, from 1993 through 2019. That's a pretty powerful snapshot over time.
It really is. So how do they track the changes, especially temperature?
Well, that was a major hurdle, actually, because long-term, continuous stream temperature data measured in the field, pretty rare. It's hard to get everywhere.
Sure.
So what they did was use a sophisticated modeling approach. They predicted summer stream water temperatures, specifically July and August averages, from 1990 all the way up to 2020.
Okay, modeling.
Yeah. And this modeling is key because it allowed them to classify every stream based on its past thermal regime. They used data from the early 1990s, 90 to 94, as a baseline.
Right, those baselines then define everything that follows. So they basically split U.S. streams into three thermal buckets, you could say.
That's a good way to put it.
You had the cold streams. These were defined as places where past summer temperatures were below 15.4 degrees Celsius. So think high elevation trout streams, maybe spring-fed creeks.
Exactly, the classic cold water habitats.
And these are the streams where any amount of warming is expected to have the most profound impact.
That's the hypothesis, yeah, because they're already adapted to cold.
Then you have the warm streams where past summer temps were above 23.8 degrees Celsius. Your lowland, maybe more sluggish, naturally warmer rivers.
Yep.
And everything in between, which was actually the vast majority of sites, they categorized as intermediate streams, kind of representing the average U.S. stream conditions.
Okay, so they've got the sites, the time period, the temperature categories. How did they measure the health or the changes in these fish communities?
Right, and they went way beyond just counting fish, abundance or how many different species, richness. Those are the basics.
Sure.
They introduced more complex metrics, too, like functional diversity.
Ah, okay, so not just how many species, but what they do in the ecosystem.
Exactly.
Yeah.
Like, do we still have the bottom feeders, the insectivores, the top predators, or are we losing certain ecological jobs, essentially?
That's a crucial layer. What else?
They also looked at site uniqueness. This measures how much a specific local site contributes to the overall regional biodiversity pool.
Interesting. So if a site loses its, say, local specialist fish and gets replaced by common generalists?
Its uniqueness drops.
Yeah.
And the whole regional community starts to homogenize, become more similar everywhere.
Okay, that makes sense.
And what's really fascinating here is how they tied these metrics back to the fish themselves, their behavior. They categorized every species by its life history strategy. Why is understanding those strategies so central here?
Because it really tells us who wins and who loses when things get stressful, like with warming or introductions. They primarily focus on two main types.
Okay.
First, the opportunistic fishes. These are typically your small-bodied species, the native minnows and dates. They have short generation times, reproduce quickly, and often called
We're with
R-selected.
weeds of the fish world.
Kind of, yeah. Think of them like weedy annuals. They're rapid colonizers, really good for fluctuating, maybe warmer environments.
Gotcha. And the other
Yeah.
type.
The periodic fishes. These are generally the larger-bodied, late-maturing species. Often the game fish we value, like salmonidae trout and salmon.
Right.
They're the long-lived, slow-growing species. And they really need stable, long-term conditions. Things like specific cool temperatures or maybe consistent river flows to succeed.
So when the environment shifts rapidly...
Their success is immediately threatened. They can't adapt as quickly.
Okay, this is where the story really takes a turn, isn't it? The study found this sharp inverse divergence between the cold and warm streams, while the intermediate streams mostly held steady.
Exactly. The contrast is stark.
Let's start with what you called the cold stream crisis. Over those 27 years, fish abundance, just the sheer number of fish in these cold streams, plummeted by a shocking 53.4%.
Yeah, over half.
And richness, the number of different species, also declined significantly by 32%. I mean, that is brutal. Are we confident this isn't just some natural cycle? It feels like a human-driven impact.
The patterns they observed, they really strongly point towards human impact. Specifically, that synergy between warming waters and species introductions.
Okay, how so?
Well, in these cold streams, the communities actually became more unique over time, or differentiating, as they put it.
More unique? That sounds counterintuitive with a decline.
It does, but here's why. It's because the small-bodied, opportunistic, non-game fishes, the native species, they drastically decreased. They were disappearing. But, and this is the crucial counterpoint, the large-bodied periodic fishes, which are often those valuable game species like trout that people stock.
Right.
They actually increased, or at least held steady in many of these same streams.
So the natives are vanishing, but the stocked fish are doing okay or even better.
That seems to be the pattern. It's likely driven by stocking programs or maybe the spread of these introduced predatory species. They either outcompete the native opportunists for food or space, or they simply eat them.
Which leads to that huge drop in the overall abundance of the native small fish.
Precisely.
Wow. That makes that 53% decline feel even more serious. It's not just a random loss. It's targeted, in a way, at the native base of the food web.
It really reframes the number, yeah.
Okay, now let's flip to the complete opposite. Warm streams. What happened there?
Total contrast. Fish abundance there increased significantly by 70.5%. And richness, the number of species, also went up by about 15.6%.
So more fish, more species. What's the mechanism driving that? Is it just the warmer water?
It seems linked to the life history shift again, but in reverse. In these warm streams, communities homogenized. Their uniqueness decreased.
Okay, so the opposite of the cold streams.
Right. Here, it looks like the small, robust, opportunistic fishes are replacing the larger periodic fishes.
Why?
Well, the opportunists seem to benefit from these perpetually warmer conditions. Maybe the water gets too warm, exceeds the thermal tolerance for some of those larger periodic species that might need slightly cooler spots, even in a warm river.
So it pushes the community towards a few warm-adapted generalists. The opportunists thrive.
That seems to be the trend, yeah. Fewer specialists, more of these hardy, warm-adapted opportunists.
So we've got this clear pattern. Winners and losers based largely on temperature regime. But the researchers didn't just stop at correlation, did they? They looked into the drivers.
They did. And first, the rate of warming itself turned out to be a really key finding.
How so?
The warming rates were far from uniform across the stream types. Their modeled water temperatures showed the fastest rise in the cold streams.
Really? How much faster?
Significantly. About 0.26 degrees Celsius per decade. That's much higher than the intermediate streams, which warmed at 0.15 degrees per decade, and the warm streams, which only warmed about 0.08 degrees per decade.
Wow, so the coldest streams are heating up the quickest.
Exactly. And that helps explain why they're in crisis, right? They often operate closer to the upper thermal limits for their native fish.
Makes sense.
So since they're warming fastest, they're losing that essential cold water habitat most rapidly. It just increases the chance that those thermal limits get crossed, especially for the native species adapted to the cold.
And this brings us back to that interaction you mentioned, the synergy. The degradation of the local non-game fish biodiversity was apparently magnified where streams were both warming and had increasing numbers of introduced or game species. That's a pressure cooker. Right?
That's exactly it. It's a double whammy. And this interaction, it has really important implications for how we interpret what's happening. It means that introduced or game fishes
often the ones managers prioritize for stocking, the ones people like to catch, can effectively mask the true extent of the native fish collapse.
Mask it. How?
Think about it.
Mm,
In those cold streams, the local, native, non-game fish abundance plummeted, right? Almost 45% per decade.
yeah, a staggering number.
But if a manager's just monitoring the total fish biomass, or maybe just the population of the stocked non-native trout, and those trout are thriving and increasing.
The overall picture might look okay, or at least less severe.
Exactly. The success in stocking those desired game fish actually hides the failure in conserving the native biodiversity that's disappearing underneath.
That is, wow. That's probably the core takeaway for management, isn't it? It challenges how success is measured.
It really does.
But, okay, while these magnitudes of change are incredibly striking, that 53% decline, the 70% increase, it's hard to ignore numbers like that. But we need to bring in the nuance. How much confidence should we really put in these specific percentages, given the known limitations of these kinds of large-scale studies?
That's an essential question, and to their credit, the researchers are pretty transparent about the limitations. They identify several key ones.
Such as?
Well, first, the temporal window. 27 years sounds like a lot, but in terms of climate change, it only represents about one full climate change oscillation cycle. It's a relatively short snapshot, ecologically speaking.
Okay, fair enough. What else?
Second, and this is a critical point we touched on earlier, they relied on modeled stream temperatures, not continuous, measured temperatures from sensors in every stream over 27 years.
Which would be ideal, but maybe impossible at this scale.
Exactly. Now, their model was highly accurate. They reported an R-squared of 0.89, which means the model predictions align very closely with measured data where they did have it. But it's still a model, not direct measurement everywhere all the time.
Right. And beyond the temperature data source.
They also acknowledged limited control for several other potentially critical environmental factors. Things like pollution levels, changes in flow from dams or water withdrawal, specific records of how often fish were stocked, or detailed land use changes right next to the streams.
So other things could be influencing these trends too.
Potentially, yes. Those are
Okay.
confounding factors. The implication isn't that the findings are wrong, but maybe the magnitude could change. It would be really valuable, as you said, to see how much of that, say, 53.4% decline signal remains once you can incorporate true temperature time series data and account for more of these broader environmental drivers in future studies, maybe more localized ones.
So the overall pattern of divergence is likely real, but the exact numbers might shift with more data?
That's a reasonable way to think about it. The powerful signal is definitely there.
Okay, so if we connect this back to the broader picture then, this divergence, it strongly supports the idea that fish communities are shaped by both the current rate of temperature change and the past temperatures they originally adapted to, right?
Absolutely. And you can really see that human handprint clearly when you look at some of the family-level trends they reported.
Like what?
Well, look at Salmonidae. That's the salmon and trout family. Their occupancy, meaning where they were found, either increased or held steady across almost all regions.
Which fits with what you said about stocking.
It strongly reflects the broad success, at least in terms of population numbers, of stocking and management programs targeting these specific popular game fishes.
Okay, what about a family that isn't typically stocked?
Conversely, look at Catostomidae. That's the suckers family. They actually decreased across nearly all regions.
Why would suckers be declining so broadly?
Well, many sucker species need connectivity. They often move long distances up and down rivers for spawning.
Ah, so dams and other barriers.
Exactly. Their decline likely implies widespread reductions in stream connectivity, probably from damming, culverts, other forms of fragmentation. That's often a result of historical and ongoing water management decisions.
So you see the direct human influence, both positive for some groups via stocking and negative for others via habitat changes.
Precisely. And mitigating these cumulative negative effects, well, the management priorities laid out by the research seem pretty clear.
What should managers focus on based on this?
Two big things stand out. First, focusing intensely on restoring riparian vegetation, especially riparian forests. Planting trees along streams.
For shade.
Yes, primarily to reduce summer water temperatures by providing shade. It's a natural cooling system.
Yeah.
Second, critically reviewing and potentially controlling the introduction and spread of non-native or introduced fishes, particularly where they might harm vulnerable local native populations.
Protecting those local populations makes sense. And looking ahead, what's the next step for the science here?
Well, the big challenge now is to start teasing apart all these interacting factors, evaluating the relative effects and the potential synergies among warming, shifting river flows, extreme weather events like prolonged droughts or heat waves, and these fish introductions, all hitting local fish communities at the same time.
Untangling that complex web of pressures.
Exactly. We need to understand those synergistic pressures better to manage them effectively.
Well, this has been a really fascinating, if somewhat sobering, deep dive.
It really has.
I think the main takeaway is just undeniable, isn't it? The fate of fish communities in U.S. rivers seems highly dependent on their starting point, their initial thermal regime. And it's those cold water ecosystems that are facing the most urgent, the most rapid degradation.
And often, that degradation is being masked, as we discussed, by the presence, even the success, of stocked game species that people value.
Which leads to a final thought, maybe something for you, the listener, to consider. We know cold streams are warming fastest. We know this warming is most detrimental when it's combined with introduced species. So, thinking about your own local watershed, what management action there might provide the biggest immediate benefit for the native fish populations? Is it riparian planting? Is it changing stocking practices? Something else?
It forces a focus on local native conservation, beyond just the popular game fish. A really important question to ask.
Indeed. Thanks for joining us for this deep dive.